Okay, so let's actually do some applications with the mean value theorem. I told you it is quite amazing, quite an amazing theorem, far-reaching implications. But what I want to do right now is let me read this question to you, okay? So it says, assume, so let's assume that you have two stationary patrol cars equipped with radar. All right, so we have a police officer here, a police officer here. And these patrol cars are 5 miles apart from each other. All right, now, it says, so a truck passes the first patrol car, or we'll say as a truck passes the first patrol car, its speed is clocked at 55 miles per hour. All right, now, 4 minutes later, that same truck passes the second patrol car, and the second patrol car clocks it at 50 miles per hour. What we're going to do is we're going to prove that that truck was speeding. We're going to prove that that truck must have been speeding during that 4-minute interval. Now, I don't know how this would. I don't know if any of you are studying law. I don't know how this would work in a case of in a law room, but I can see somebody grabbing some markers and a whiteboard and doing what we're about to do now. Ready? So let's start. Let's collect some information. So let's look at our time. So we have at time 0, right? That's at time 0. Let's establish that we'll say distance is 0, right? Because that's the first police officer clocks this truck driver. Time 0, distance 0, and we'll get back to the rate in just a second. Now, at time 4 minutes, so 4 minutes later, I'm going to actually get rid of the units. I don't want to clutter. So at time 4, the distance would be 5, right? 5 miles. So I am actually going to go back and add the units now that we're done discussing them. So at time 0, we have a distance of 0 miles. At time 4 minutes, we have a distance of 5 miles. All right. So far, so good. So let's go ahead and write the speed at each of those times. Ready? So at time 0, that would be distance 0 for us. The speed was clocked at, what did we say? 55 miles per hour. Now, 4 minutes later, that truck has moved 5 miles. And again, another patrol car clocks this truck driver at 50 miles per hour. So our first step here is going to be to find the average rate of change. All right, no calculus needed. The average rate of change, that's the rise over the run formula that you've been using probably since middle school. So the first step is going to be to find the average rate of change. Now, what I'm going to do is look, I have time given to me in minutes and I have speed given to me in miles per hour. So either I'm going to have to change the minutes to the hours or the hours to minutes, right? In order to make sense of this. So let's see if I can set this up. So okay, I'm coming up there. I know I'm coming up there in just a second. So 4 minutes. I'll come off to the side here. So what we got 4 minutes. Let's change that into hours. So 4 divided by 60. Right, that would mean that was that 1/15 of an hour. You with me? So 1/15 of an hour, 4 over 60. Okay, so let's set up the formula for the average velocity. How would that look? So the average velocity, right? That, like I said, it's going to be the rise over the run. Only in this case, I mean, if you think about it, we have it's going instead of delta y over delta x, right? Because we're dealing with time and distance and speed, right? It's going to be what? It's going to be delta d, distance, over delta t. I hope that makes sense. The change in distance divided by the change in time. Now I'm gonna listen. If you know what I just did, you can skip for a second. Distance is equal to rate multiplied by time. We should say distance is equal to the average rate multiplied by time. That means the average rate is equal to distance divided by time. I hope that makes sense. All right, so in this case, we're going to have, let's start with the first, it's going to be, let's start with the distances here, right? So that's what I meant by setting up the points. So, okay, so in this case, at time 0, distance is 0. Now, at time 4 minutes, which we're going to write as 1 over 15, distance is 5. So, ready? Let's go ahead and do our rise over run formula. So that's going to be first the change in distance, so that's 5 minus 0, divided by the change in time. Remember, we're using hours, so 1/15 minus 0. So that's just 5 over 1/15. All right, if you get out your calculator, you'll figure out that 5 divided by 1/15 is 75. Right, so this is in miles, this is in hours, so that's 75 miles per hour. Wait a minute. So the average velocity of that truck was 75 miles per hour. Now, the idea of the mean value theorem, right, is to show that by definition, there must, so if let me draw it here. So if this is the average velocity of 75 miles per hour, then by definition there must have been some point where the average velocity was equal to the instantaneous velocity. Right? So as long as we assume the position function is differentiable, the mean value theorem assures us that look, you notice that all you did was find the average? Can you imagine someone, you pull someone over and they say, maybe my average velocity was 75 miles per hour, but you didn't clock me speeding? Well, the mean value theorem guarantees us that if the average velocity, if again, as long as those conditions are met, it guarantees us that there was some point and there was somewhere during those 4 minutes where that truck driver was going, where the average velocity, 75 miles per hour, was the instantaneous velocity. It guarantees us that this individual was speeding. All right. I know, that's incredible. Probably the greatest thing you've ever done in your life. Let's do one more of these guys. Let's do this. So it says, all right, so now I think in this case, we're gonna be removing some object from a furnace. Okay, so it says, when an object is removed from a furnace and placed in an environment with a constant temperature of 90 degrees Fahrenheit, its core temperature is 1500 degrees Fahrenheit. Okay. Now, 5 hours later, the core temperature is 390 degrees Fahrenheit. All right, wait a minute. So let's start. So at time, let's do this. So let's set this up. Ready? So let's see if you agree with this. At time 0, that's when you first pull this, I don't know, whatever it is that you're cooking at 1500 degrees Fahrenheit. When you first pull this object out of the furnace, at time 0, its temperature, right, is 1500 degrees. All right, now you put it on a table, say, where the temperature in the room is 90 degrees. You come back 5 hours later, and you take the temperature of this object again, and now the temperature is 390 degrees Fahrenheit. So what do they want from us? They say, explain why there must exist a time in the interval, right? So in the interval from 0 to 5 hours, explain why there must be some time in that interval when the temperature is decreasing at a rate of 222 degrees Fahrenheit every hour. Well, this might look gimmicky, and all we have to do, okay, is assuming that all these conditions are met, all we have to do is find the average. If you can find the average change in temperature every hour, then we're automatically guaranteed that there was an exact time where it was decreasing at that rate, right? So your steps are always the same here. We're going to find the average change, right? So in this case, it's the average change in what? In temperature. That's not temperature. In temperature per hour. Okay, if you read average change, rates of change, you should be thinking rise over run or slope formula, right? So let's start. Let's start with the average change in temperature per hour. So the temperature changes from, I will write this as points, right? So you got 0, 1500, and then you have 5, 390. Right, so you can, if you want this, you can say this is x1, y1, x2, y2. If that way that confuses you thinking about different variables on the axis, then let's run it this way. Ready? So this would be 390 minus 1500 over 5 minus 0. Okay, So if you grab your calculator and do a little bit of arithmetic, you will get negative 222 as a result. Okay, so a lot of students right now, they don't know how to answer the question. They're like, Professor, I guess this is cool, maybe, or it seems pretty easy, but this is the average change in temperature in degrees measured in Fahrenheit per hour. But they feel like, I don't really know how to answer. Well, how do I answer the question? So at this stage of the game, see this bullet point, you make a statement. So let's read what I highlighted. Explain why there must exist a time in the interval when the temperature is decreasing at a rate of 223 degrees Fahrenheit per hour. So at this stage, you would say something like, by the mean value theorem, there exists a time okay, so there exists a time, we'll call it t, over 0 to 5, right? By the mean value theorem, there exists a time t in between 0 and 5 such that T of T, meaning the temperature at that time, is equal to negative 222 degrees Fahrenheit per hour, right? I understand that you're not used to answering a math question with a paragraph, or I get it. But you're basically just saying, look, the mean value theorem guarantees it. That I don't know what time, right? It could have been an hour later or 2 hours after you put this item on the table. But there was a time somewhere in there where the temperature was dropping at 222 degrees Fahrenheit for every hour. All right, I am going to conclude, and I will see you soon.